All right. You're going to find the volume of a solid bound by a region of curves about a given axis. All right. We should be able to picture in our head y equals square root of x and y equals x. And we're going to go about the axis x equals negative 1. So to make a quick little sketch so we kind of see it, we know y equals x is just a 45-degree line. We recognize that the square root of x is a little curve. And so our region is right there. And this is not a great picture. Now we could go to the solver and write, we could go to the solver and say, hey, y equals y, so square root of x equals x, and x minus square root of x equals 0. We could type this in the solver and tell us to do it. Or we could just use our heads and check some integers. Where are the intersection points of these two equations? They're obviously at 0. They're obviously at 1. Right? Just check the integers. Just because you can use your TI calculator doesn't mean you should. I just guessed and checked integers. I just tried 0, got 0, 0, 0, right? What's the next integer? 1. Oh, look. It worked. And that is much faster, all right? So we use that knowledge. Now we're going to rotate that across this axis, x equals negative 1. All right. This is parallel to the y-axis, so it can't be dx. It has to be dy. So our equation this time, our general form is going to be what? Volume is equal to the integral from some limit a to b, the cross-sectional area with perpendicular to the y-axis, dy. So our slices are not perpendicular to the x. Our slices this time are right here. And we're going to rotate that little golden region about the green axis I have here at x equals negative 1. So again, the million-dollar question, what's the cross-sectional area of this? It is a washer. It is a washer. And like a broken record, every single time, I will always draw the picture, RO, the other radii is RI. We can see that the area in the washer, right, is pi r O squared minus pi ri squared. We have been doing quite a few of these. So I'm going to say volume equals, boom, and I'm going to put the pi out here. That was a good idea. List I had yesterday. Let's skip that step. And we get r0 squared minus r outside minus r inside squared dy. Now everybody, we gotta be crystal clear about this right now. It's the origin is one of the points, 0, 0, right? The other point is 1, comma 1. The limits of integration, because we're going dy, have to come off the y-axis. They're the same on this problem, okay? But we're going to put in...
Should we just backtrack to
yep.
It's 1, comma 1?
Yeah, it's 1, comma 1. So since we're integrating with respect to dy, we have to pull the limits of integration off the y-axis. It is 0 to 1, okay? But it's not this 0 to 1. It's the vertical set. All right, right there. All right. So we have that, but now here's the problem. I can't integrate r outside and r inside with respect to y. I have to convert these variables into some function of y. So that's our next step. If I blow up, or look in here, maybe I can blow this up. Boom. All right, wow, what a horrible picture. All right. I think my RO goes from the green axis to the red line. You guys agree? I think my RI, I'm sorry, that's the radius inside. I think my radius outside goes to the blue line. All right? So in this case, all right, it's going to be the right some value x to the right, all right? Going back, and I'm going to go back to an entire page. So I think my outside radius here is going to be some x distance from the origin minus a minus 1. All right? So think about it. It's 1 plus the x distance, but I don't want the x distance, do I, everybody? What do I want? I want the y, but what does y equals x this time? So what's it become? It becomes y plus 1. On the inside radius, it goes to the other function. Okay? So what the other function is, still some x distance to the right. This is where it gets hard, okay? Still minus 1. But this time we got to use this function. Uh-oh. It's not x equals yet, is it? We just got to square both sides. What's x equal? X equals y squared. Now it's above the x-axis, so we know it's positive, right? So we're okay. So instead of x here, we can write this as y squared plus 1. Guess what I now have? I have my RO and my RI. This is a nice calculator problem, you guys agree? Now this would not be a bad one if it was on a hand section either, all right? Because RO is just y plus 1 squared. RI is just y squared plus 1 squared dy. You think about this. These are just binomials. They're not going to be that hard if you had to square them out. I'm going to pause the video. Let's try to type in the calculators, all right, and see if we can get an answer for this and know what the volume of this solid is. And I'll put the calculator up top. So everybody, when I do it in my calculator, I didn't include pi. Up here you can kind of see it right here, right? I just did it here. So I get volume equals pi times, it looks like 0.46 repeating. We know a repeating decimal will be a rational number. You can probably figure out the fraction. 7/15. So the volume of this is 7/15 pi. And if you multiply it out, that's fine. Just go to 4 decimal places. If you take the answer times pi, 1.466. I agree. 4 decimal places. And everybody, we just flew through, if you think about it, compared to where we've been, we just flew through finding the volume of a region. I think we're getting better at this. The calculator does help. Keep practicing. The AP is coming.